So in this video, we're going to talk about a very specific characteristic that derivatives have, specifically that they're linear operators. So first we'll address what linear operators are. Why is this characteristic beneficial when we're taking derivatives? But then what do we need to be a little cautious of when we're taking derivatives? So this discussion of linear operators is going to be specific to students in a Calculus 1 course. They're just learning derivatives. They've heard about this property. What is it going to be useful for them? And then what is it going to cause them to have to be a little bit more cautious of? So a linear operator is any operator that preserves the operations of addition, subtraction, multiplication by a constant. So what does it mean to preserve the operations? I think we'll make more sense out of that when we look specifically at derivatives in a minute, but let's talk about a little bit more of a familiar calculation from math, specifically a square root. Square roots are not linear operators. The reason why square roots are not linear operators is because I cannot take the square root of 9, add on the square root of 4 in order to get the answer to the square root of 9 plus 4. In other words, the square root of 9 plus 4 under a single root does not equal the square root applied to each number separately and then added together. The square root calculation does not preserve the operation of addition. Similarly, it does not preserve the operation of subtraction, and it doesn't preserve the operation of multiplication by a constant. A linear operator has all three of these characteristics. Essentially, it means I can apply the calculation to each individual entity and then add the results, subtract the results, or just copy the constant into my result. Derivatives are linear operators. So if you look at this statement here, f of x and g of x are differentiable at a value x, and c is any constant. If I'm taking the derivative with respect to x of f plus g, I can find that by simply taking the derivative of f and adding the derivative of g. Similarly, with subtraction as the operation between the two, I can simply take the derivative of f, subtract off the derivative of g. If I have a constant multiplying the function that I want the derivative of, I can copy that function into my derivative and put the derivative of the bigger part of the function right beside it. These characteristics are extremely beneficial. They allow you to take quite a few shortcuts when you're computing derivatives. We'll show that within an example on the next screen. Here's what is not within this list. There's nothing that says with multiplication between two functions, I can simply multiply the derivatives together to get my answer. With division as the operation between the two functions, there's no property existing here that says I can just divide my two individual components to get my derivative. These properties do not exist for derivatives. This is what you have to be careful of. We'll again talk about that in a specific example a little later on in the video. So here's the first example that I want to try to go through. So we're going to find the derivative of f of x. Now, this video assumes you already know what the power rule for taking derivatives is, which simply means we're going to multiply by the power and subtract 1 from it. Now I am going to adjust this square root into a power so I can apply the power rule a little bit more effectively. And I'm going to take the derivative of both sides of this equation. When I take the derivative on the left, I get f prime. So taking the derivative of f of x just gives me f prime the whole way down. If I'm taking the derivative of this quantity on the right, if I want to explicitly apply those properties that we looked at on the last screen, I can adjust this derivative of the sum into the sum of two separate derivatives. I can then take this constant and bring it out in front and put the derivative of x to the 6th right beside it. I can take this constant, bring it out in front, and put the derivative of x to the 1/2 right beside it. So I copied this constant, derivative of x to the 6th, multiplied by the exponent, subtract 1 from it. Copied this constant, derivative of x to the 1/2, multiplied by the power, subtract 1 from it. If you simplify this, 2 times 6 multiplies to 12. That'll be the coefficient of x to the 5th. 3 times 1/2 will multiply to 3/2. That'll be the coefficient of x to the negative 1/2. This is about as lengthy as you can make this particular derivative. Here is the main reason why the derivative being a linear operator is an extremely beneficial property. I can get straight from the top line down to this derivative line simply by multiplying this coefficient by that exponent, get directly to 12, subtract 1 from the exponent, directly to 5. Now I'm looking at this line, I guess, multiplying this coefficient, 3, by this exponent, getting to 3/2, and then subtracting 1 from that exponent. I'm guessing your teacher, your professor, is not going to require for you to show all of these linear operator steps being applied like I've done within this example. You're probably going to be able to go straight from the beginning to the answer. So these properties existing are extremely beneficial because they basically mean we do not need a special rule when taking derivatives for the operation of addition, the operation of subtraction, and the operation of multiplication by a constant. Now, what this also implies, we are going to need a special rule for multiplying two functions of x. We are going to need a special rule for dividing two functions of x. So in this next example, we want the derivative of f of x. Here's the function, so it's a binomial times a binomial. This is two functions multiplied together. Look at the bottom of the screen first. This is the wrong way to do this. The derivative of x is 1. The derivative of 1 is 0. The derivative of 3x squared is 6x. The derivative of 4 is 0. I multiply these two sets of parentheses together. I get the answer of 6x. There is not a property of derivatives that says when you're multiplying two functions together, just do the derivative of each function and multiply the results. There is a property that says we can do that for addition and subtraction. There's not a property that says we can do that for multiplication. So how would you go about taking this derivative if you don't yet know what's called the product rule, which I'm sure you'll be uncovering soon within your calculus course? Well, you're gonna expand this. You're gonna FOIL this out. So first times first will give me this. Outer times outer will give me minus 4x. Inner times inner will give me plus 3x squared. And then last times last will give me minus 4. Now, if I take the derivative using the shortcut that we identified within the prior example, I'm just going to take the derivative of this by multiplying this coefficient by that exponent. That gets me directly to 9. Subtract 1 from the exponent. This is minus 4x to the first. I'm going to multiply the coefficient of negative 4 by positive 1. It stays negative 4. If I want to put an x to the 0 beside this 4, I can, but x to the 0 is 1, so I don't have to show that. Derivative of 3x squared, multiply the coefficient by the exponent, subtract 1 from the exponent, and then the derivative of a constant is going to be 0. We don't need a special rule for subtraction, which we have in two spots, addition, nor multiplication by these constants. Therefore, we were able to take the shortcut after we resolved the issue of having a product. Last example here, we want the derivative of this function. The work in blue is correct. We'll talk about that momentarily. Here's the wrong way to do this. There's not a property of derivatives that says I can find the derivative of one function divided by another by taking the derivative of the top function and dividing by the derivative of the bottom function. That's what I've tried to do here. This simplifies to what you see on this line here. There's not a property of derivatives that allows us to do this. You would need to use the quotient rule in order to do this derivative successfully, which, again, you'll probably be uncovering that maybe the same exact day you uncover the product rule. How do you do this if you don't yet know the quotient rule? Well, I can divide all three components of this numerator by x. 4x squared divided by x, subtract the exponents. 2 minus 1 gives me x to the first. 3x to the first divided by x to the first is 3x to the 0. I don't have to show that x to the 0. 2x to the 1/2 divided by x to the first, subtract the exponents. I'm going to get negative 1/2 as the new exponent on x. I have subtraction, I have addition, I have multiplication by a constant in a couple of spots. I don't need a special rule when I take derivatives containing those operations, so I'm just going to take the derivative of all of these components. Derivative of 4x to the first is 4x to the 0. The derivative of the minus 3 is going to be 0. This is a little weird. Probably have done this. Definitely will get used to this as you take derivatives. The 2 has a positive sign associated with it, but I'm going to multiply it by a negative exponent. So I'm multiplying this coefficient of positive 2 by this exponent negative 1/2. That's going to give me a new coefficient of negative 1. So rather than plus negative 1, I just changed the operation to subtraction. And then I'm subtracting 1 from that exponent. Clearly this answer does not equal the answer that we got down here. So why is being a linear operator a significant property for derivatives to have? We can take the shortcuts that we took in the examples that we did through the correct process within this video, we cannot take the shortcuts we took with the product and with the quotient. Product rules and quotient rules will be discussed in your calculus course, and you'll be able to then use those as alternate ways to find the derivatives of those final two examples.